Okay, good morning, students. Those who have just connected, please you can type good morning so that we can start the class. Like I mentioned, the class will be on Moodle, so we are supposed to start now. So please, if you are able to hear me, then so that we can start, you can just type to say good morning, sir. All those who are able to hear me, you can just type. That's great. That's great. Okay, so we can start the class now. So we are looking at applications of integration. Like I mentioned yesterday. Yesterday I couldn't meet in the afternoon. I was a bit committed. Somewhere I was tied up. So I'll start with first the application of integration. I think in the next, maybe we'll not even reach at 11 hours. We'll end the class will finish as fast as possible because the type of applications that you'll be looking at are just the basic applications of integration. Now, the detailed, we have also those who will be continuing with maths and engineering. Basically, you're going to learn mathematics in second and third year where you do triple integrals. You're going to do on how to calculate the length. You're going to understand why when a wheel is rotating, you see something like a solid. For example, the wheel for the vehicle, when it's rotating, what you see, you don't see those rims. What you see is just something like a solid. So you're going to learn those things in third year, which involves applications of integration. You're also going to learn something to do with centroids. Or some of you who have done physics, those who will be doing physics, you're going to learn centroids. There are also a lot of applications of calculus or rather integration and differentiation that you're going to learn in second year. But for now, we're just going to look at the basic properties of integration. So having said that, so this is how we are going to do it. Now, under these same basic properties of integration, what you're going to look at are these which are beamed on the nodes on the board, which includes we are going to look at which we are saying applications of integration. Now, under this topic or rather subtopic, we are going to look at, section of this chapter of under integration. We are going to look at area bounded by the curve y equal to f of x. Now, this area which is bounded by this curve, we have a function which is y of a function of x. Now, we are going to look at a situation where this area is bounded either by the curve and the x-axis. We are also going to look at the situation where this area is bounded by the curve and the y-axis. Now, like I texted you to say you can check on Moodle I've just updated the notes on Moodle early in the morning. Today I updated them, so you can just download those notes. Of which you have the tutorial sheet your tutorial sheet that you have. There is the down part where they have given you to calculate the areas of the region bounded by a cave and some points. Now, so these are, and also we're going to look at the volume of slicing and rotation about an axis. So we're also going to look at the volume of rotation in shorts, which from there now we call it the end of the class. Now, so having said that, so we are saying in this chapter, we will explore some of the applications of definite integrals. So basically, under the applications of definite integrals, we concentrate more on area and the volume. Okay, so there is under the application of definite integrals, we use them to calculate the area of the area of a cave, or between a cave and the x-axis or the y-axis. It also helps us to calculate the volume of solids and also the length of the cave. Now, for calculating the length of the cave, you're going to do that in second year when you do the integration and derivative of functions of several variables. Now, so having said that, so we are saying in most cases, most importantly, the application of definite integrals is finding the area under the curve y equal to f of x. Maybe let me just let me beam. Now what happens is, but then up to now, such areas could be found approximately by, for example, counting squares or by the trapezium rule. What do we mean here is this. Maybe let me just go back. Let me just beam the board so that I can explain properly here when it comes to this concept. Now, okay, so if you look at when you were in secondary school, at high school level, when you are doing your high school, this is what happened. When you were given, you remember the so-called graphs of polynomial. Under the graphs of polynomial, this is what you were doing, which I'm still remembering. So under the graphs of polynomial, so they will give you a curve. Okay, so they will give you this curve. Maybe the curve will come like that, then it will go like that. Okay, now what will happen is, then they will ask you to say, find the area bounded by the line. For example, they will say x equal to 2.5 and the line y, for example, y equal to 1 and the curve. So what you are doing, I remember in secondary school, is that you have sketched this on the graph paper, and then what you usually used to do is you used to count the number of boxes, which are the number of squares which are inside, which are bounded by the curve, by the line x equal to 2.5 and the line y equal to 1. So all you used to do was just to count the number of squares. Or you use the trapezium rule. I think you used to sketch a trapezium. Within that, you sketch something like a trapezium, and then you approximate your area. So this is also what you used to do. Now, this time around, we don't need to get worried to say, how can I find this area? Because if I count the complete squares, there is a very quarter of a square that is remaining, which you never used to count, moreover. So that's why I used to say the area bounded by the curve and the line y equal to 1 and x equal to 2.5 is approximately equal to. That's what you used to say. You never used to say is equal to, you just used to say is approximately equal to. Now, this time around now when using calculus, so using calculus will now help us to calculate the exactly value, the exactly area of this region bounded by the line x equal to 2.5, y is equal to 1, and the curve. So this curve is just equal to y equal to f of x. So using calculus, you can calculate the area or the volume of any kind of a shape, no matter how ugly this is, even the area of this, the area covered by the stone. If you have a stone, which I think you used to say you can't calculate its area because it's irregular, it's an irregular shape. But when you use calculus, you can calculate any area of any object of whichever form. I guess everyone is following. So someone asked me last time, sir, where do you use calculus? Where do you use maths? So let me tell you, calculus has a lot of applications. If you recall you say the centroids, or how to calculate the volume of an object, of a rotating object, it's like you have a fan. One thing that you need to understand is what volume will it cover when it starts rotating, or what area will it cover when it starts rotating. That will tell you to be careful that if I go closer to this, it will cut me. So you have all these kind of concepts for calculating the area. So you look at the vehicle, some of you maybe have vehicles, or some of you have parents with vehicles. If you look at the blue book, you find they have put the length, the breadth, the height, then they'll give you maybe the area that vehicle has. Now, if you look at this vehicle is in a shape in such a way that you can't even manage to calculate its area. Now, the question is, then now, how did they come up with that area? So they came up with that area by using calculus, by using the definite integrals. So all you need is to maybe put a ruler and then you find how long is this vehicle. Once you do that, then you say how high is this vehicle. From there you are done. Then when you use calculus now, you form an equation of an x variable. Then you compute the area that this vehicle is going to cover. Okay, so now let's look at the first one, which we are going to say area bounded by the curve above the x-axis. If you've not downloaded the notes, please make sure that you download the notes, because like I mentioned last time, I'll be writing on the board. So make sure that you go to Moodle and download the notes. So the first part is that is of this chapter, which is I'll call it 1.1. I hope you're able to see my markup. 1.1. We are going to look at area bounded by the curve, bounded by the curve area bounded by the curve y equal to f of x, by the curve y equal to f of x above the x-axis. This curve is above the x-axis. Okay. So you have the notes, like I mentioned. So I'll be cruising in that scenario, because you already have the notes. Every one of us has the notes. You've downloaded the notes. Now, so this is the first part of our. So we are saying, So we are saying if f is continuous, throughout the region, if f is continuous throughout the region, this region AB, supposed to be, if f is continuous throughout the interval, so we have a function f which is continuous in the interval AB, and the part of the curve, and the part of the curve and the part of the curve y equal to f of x, and if the part of the curve y equal to f of x, now y is equal to f of x lies above the x axis, then the area between that part, the area between that part, then the area between that part and the x-axis and the x-axis from x equal to A to x equal to B is, now the area of that region from x equal to A to x equal to B is given by the integral from A to B. So area of that region, so area is equal to the integral from A to B of f of x dx. So it's the integral from A to B of f of x dx. Now, how does this region really looks like? This is how the region looks like. So you have something like this. An example of such a region is the one I'm sketching here. Okay. So, for example, you have your curve that goes like that. This curve is y equal to f of x. So the curve is y equal to f of x. And then now you have a point here which is point A and a point here which is point B. So this is the x-axis, this is the y-axis. Now what they are asking you to find is the area of this shaded region. So we are saying the area the area of the region which is bounded by the curve y equal to f of x, and the x-axis which is bounded by the curve, the x-axis, the line x equal to a and x equal to b is just the integral, the definite integral of the function of the curve f of x from the point A to the point B. Here, the reason being, why the area is written in that form, look at this situation that the shaded region, this shaded region is below the curve. It's below the curve. Okay, so because the shaded region is below the curve, as such, the area of this region, which is below the curve, or which is bounded by the curve y is equal to f of x, x equal to a, x equal to b, and the x-axis means y equal to 0, is given by this formula. So it is just the definite integral of that function. Okay, now let's look at an example. So I'll be looking at a single example. There are about 2 examples in each part of the topic, but I'll not be looking at all of them. I'll just be looking at one at most of the times. Okay, now the first example is I'm going to wrap this. Okay, so our first example says, which is example 2 from our notes. Our first example is example 2 from our notes. And the example reads, it says, find the area of the region bounded by the curve. That is example 2 from our notes. The example says, find the area bounded, I'll not be writing because you have the notes, so I'll just be reading it. Find the area bounded by the curve, y, our curve is y, which is equal to 8 plus 4x minus x squared. So, and the x-axis. So you are given this question in an exam or rather in the test, and then they're asking you to compute the area of the region which is bounded by this curve and the x-axis. The first thing that you're supposed to do is that you're supposed to sketch the graph. When you sketch the curve, the graph of this curve, then it becomes so easy to compute your area. If you fail to sketch it, then it will be difficult for you to calculate the area of which they are looking for. Now, if you look at, the first thing that you should do is you need to find the limits of integration. How can you find the limits of integration? So we need to find the limits of integration by solving. Now, the limits of integration are the values of x. We need to find the limits of integration by obtaining the points, by obtaining the points where, by finding the points where the curve this curve, where this curve crosses, or you say meets or crosses the x-axis. Now, when will this curve cross the x-axis? This curve will cross the x-axis when the curve crosses the x-axis. So that is when the y value is equal to 0. So basically, for you to find the limits of integration to this, because when you want to calculate the area of the area bounded by the region and the x-axis, what they're asking you is to find the definite integral of that curve within those limits. Now, to find the limits of integration, you need to find the points, the x-coordinates at which this curve meets the x-axis. Now, to do that, those points at which this curve meets the x-axis, the y value will be 0. So basically, we need to solve when y is equal to 0, then our 8 plus 4x minus x squared will be equal to 0. Now, when we solve this one, you observe that 0 will be equal to, which is equal to 8 plus 4x minus x squared. And when you factorize this, you are going to get 4 minus x, then you get x plus 2. Now, which implies x will be equal to 4, x will be equal to negative 2, and x will be equal to 4. So, these points are your points of integration. So, these are your limits of integration. They did not show you the limits of integration, but they just told you to say the area bounded by this region and the x-axis. Now, if you wanted to sketch, I think in first semester you did the quadratic functions, and you were sketching quadratic functions. So this is a quadratic function. Maybe the issue that we need just to find is the turning point, isn't it? Which is negative x is equal to, is it b over 2a, when then you substitute it there. So basically your graph, so just for argument's sake, if you sketch your graph before you even start making the calculations, let's try to sketch our graph. So if you recall, so we have negative 1, we have negative 2, we have negative 3, so we have 1, we have 2, we have 3, and then we have 4. Okay, so we have 5. Now, so we have 1, we have 2, we have 3. Now, what is our turning point? Please, can we compute first? We find our turning point. Our turning point occurs when x is equal to what? We have mathematicians here, please. Our turning point occurs at the point, the x coordinate is equal to what? X is equal to b over 2a, isn't it? So the turning point occurs when x is equal to b over 2a. So your b is of is it x equal to negative, should be negative b, right? Yeah, negative b over 2a. Then your b is 4, our a is negative 1, so we are going to have a 2. So the x coordinate of the turning point will be a 2, and the y coordinate of the turning point. So if you put a 2 here, you have a 4, we have 8, 16 minus 4 to give us a 12, isn't it? So our turning point, maybe I'll just say we have a 12 there. So about say 1, 2, 3, so we have a 12 there. So our turning point will be somewhere there. When we need to cross the y-axis, to cross the y-axis at 8, so we'll have something, a graph that will come like that. So this is just a skeleton graph. It's not really unique because I'm just giving you a skeleton of the graph. So this is how our graph will look like, which is y equal to 8 plus 4x minus x squared. I hope my sketching is okay. So now, the area which they are asking us to find is this area under this curve. So the area which they are asking us to find is this area which is bounded by this curve and the x-axis. So it's the area bounded by this curve and the x-axis. Now, because this area is under this curve, then using the formula of the area under the given curve, it means that we are going to have, I'm writing this part. So now, having found the limits of, so the limits of integration is x equal to 2 and x equal to, x equal to negative 2 and x equal to 4. So now, it means then the area which is bounded by that region, so I'm using capital A, which is the symbol for area. So the area now, bounded by the curve and the x-axis is just equal to the integral. Using that formula, it's the integral from a to b. Now, in this scenario now, our a is equal to 2, negative 2. Our b is equal to 4. So we are going to have negative 2 to 4 of our function is 8 plus 4x minus x squared dx. When we integrate this by linearity properties, when we integrate this using the linearity properties, this is equal to 8x plus, when you integrate this, it will be x to the power 2 over 2. So it will be 4 times x to the power 2 over 2, so to give us 2x squared. And when we integrate this, it will be minus x power 3 over 3. Now the limits are from negative 2 to 4. Hence, now, when we push in the limits, please, then someone was asking, I equated the equation to 0 because we are finding we are looking for these 2 points where the graph crosses the x-axis. The point where the graph crosses the x-axis, the y-coordinate is 0. Okay, now, when you do, I don't need really to do this because you understand what you're supposed to do. So using the fundamental theorem of calculus, so this is equal to, like, we put 8 times 4 minus 2 times 4, which is squared, minus 4 to the power 3 over 3, using the fundamental theorem of calculus, then minus, you change the limits, 8 times negative 2, plus 2 multiplied by negative 2 to the power squared, negative 2 squared, then minus negative 2 to the power 3 over 3. Now, when you simplify this numerically, what you're going to get is 144 divided by 3, which will give us 48. Now, what type of units are we supposed to use here? Now, we don't know whether this area that we have been given, we are going to calculate it in centimeters or kilometers or what, but because the units are not specified, so you just write units squared. If you don't write units there, you just write 48. I'll tell you 48 what? Is it number of animals, or is it number of birds, or number of people? So you need to make sure that you say units squared. That means it's representing the area. If you feel that how can I find the limits? How can I find the limits? Now, what you need to do, you just need to sketch the graph. Now, for you to sketch the graph, you need to solve that function. You need to solve that function y equal to 8 plus 4x minus x squared. You need to substitute where there is y 0 so that it helps you to find the x-intercept. The y-intercept occurs when x is equal to 0, which will be 8. The x-intercept occurs when y is equal to 0, which is negative 2 and 4. Then now, your limits of integration are the points at which this graph is crossing the x-axis. Now, let me tell you something here. It's not always that your limits of integration will be at the point when the graph will cross the x-axis. There are at times when the limits of integration will be different. In most cases, you find it's given. Okay, so please let's not confuse ourselves. So depending your procedure or your approach of finding the area bounded by the curve and the x-axis depends on how the question has been phrased and the type of information that is given in the question. Not that the way I've solved this example is the same way that you solve the next example just like that. No. All right. There is example number 3 from our notes, which I'm going to leave this as an exercise. Please find time to go through it and then you solve it. So I'll go to the other part where we are finding area bounded by the curve. Now this curve, and this time around, it's below the x-axis. So I'm wrapping my board. Okay. Okay, so now let's look at the area bounded by area that is 1.2, area bounded by the curve y equal to f of x, but now this time around it is below. The curve is below. Our curve now is below the x-axis. Our curve is below the x-axis. So we are now looking at the area bounded by this curve, which is below the x-axis. So we are saying, if I'm not going to write much because you already have the notes. If, for example, f is continuous in the region AB, okay, and part of this curve and part of y equal to f of x is below the x axis, then the area bounded by that part the x-axis, that part, and the x-axis from x equal to a to x equal to b is given by area is equal to the integral from a to b of f of x dx. So it's the negative. So when the curve lies below the region, so this curve is lying. So if you look at this curve is lying above the shaded region. Now, if the curve lies below the shaded region, then the area bounded by that region which lies above the curve is the negative of the integral of that curve with respect to x from a to b. So it's the negative. Okay. So an example of this kind of a region is a region which is of this format. So any region that lies above the curve, when you want to find the area of that shaded region which lies above the curve, what you need to do is you take the negative of the integral. So an example of such kind of a region is the region I've sketched here. So for example, you have this region. So we have y, we have x. So you have maybe this region that comes like that, then it goes up like that. So this is the curve y equal to f of x. Now, what they want you to find is the area of this region, which is, now if you look at this region, so they're asking us to find the area. This region has okay, so this region, if you look at it, it's above the curve. Okay, the curve is below the region. This region is bounded by the curve and the x-axis. So because this region is bounded by the curve and the x-axis, as such, its area is equal to the integral from point A. So then we have point A here, point x equal to A, and then here we have x equal to B. So from point A to point B is equal to the negative of the integral from A to B of f of x dx. Okay. So let's look at some examples that involves the area of a region bounded bounded by the curve and the x-axis. Okay, this is example number 5 from our notes. We can check example number 5 from our notes. The example says, find the area of the region bounded by the curve. So our curve is y equal to x squared minus 3x. Our region is y equal to x squared minus 3x. So what we're supposed to do is, if we sketch, So if you look at the curve, this curve meets the x-axis when at a point when y is equal to 0. It meets the x-axis at a point when y is equal to 0. So that is when 0 is equal to x squared minus 3x. So solving for x in that equation, solving for x. So if we solve for x, solving for x gives, when we solve for x, gives that we are going to get x is equal to 0, and so when we solve for x, we are going to get x equal to 0 and x is equal to 3. Okay, so graphically, graphically, this region will look like this. This region will look like this. Okay. So this is the region we are talking about. It will cross the x-axis at this. So this is y equal to x power 2 minus 3x. So using the formula for the area of a region bounded by the curve, which is below, the curve is below the shaded region. So area is equal to the integral, the negative, so it's the negative of the integral from 0 to 3 of f of x. Our f of x in this scenario now, it is x squared minus 3x dx, which will give us, when you look at this, we are going to get x power 3 over 3 minus 3x squared over 2. The limits are from 0 to 3. So when we solve this, when we compute this, basically each one of us understands what goes on. So using the fundamental theorem of calculus, this is just equal to 3 to the power 3 over 3 minus 3 multiplied by 3 squared over 2, then everything minus 0 cubed over 3 minus 3 times 0 squared over 3. When you simplify this, what you're going to get is 27 over 6 units squared. Okay. So this is what you're going to get. So after simplifying this, then you're going to get that. Okay, so that is all about the area bounded by the curve y equal to f of x, and the x-axis where this curve is below that region. So the next part that we'll be looking at, so the next part of our session now is the next part that we should be looking at now is the area bounded by So the next thing that we'll be looking at is the area which is bounded by the region, that is 3 point. So area bounded by the curve y equal to f of x. So let's now look at the area bounded by the curve y equal to f of x, which this curve is partially above and partially above the x-axis and partially below the x-axis. So we have a situation where we have this curve, like if you look at the sine and the cosine function, which are partially above the x-axis and below the x-axis, above the x-axis, below the x-axis. So it's just like that. That's how it works. So now, if you have such a scenario, so these are the situations that we are looking at. So the area bounded by the curve y equal to f of x. Now this curve is partially below the x-axis and also partially above the x-axis. So maybe I'm just going to read. So if we have a function, if f is continuous, maybe I've written a lot, continuous in the region, through the region AB, and such that this function, such that the same function y equal to f of x, the same function y equal to f of x the function y equal to f of x lies partially above and partially below the x-axis, then the total area, then the total area is sorry for, I think there's the total area is, so area will be equal to the integral from A to B, okay, of f of x, where this region is, where at this, in this interval, the region lies above, then minus the integral from B to C of f of x, where through this region, sorry, I was supposed to write here A to C, not A to B. It's supposed to be A to C. From B to C, the curve lies below. Yeah, there's someone who has asked a question to say, are we not supposed to put the negative sign? Yes. We're supposed to put that. I just missed it out. Let me go back to the solution. So we're supposed to put here, okay, sorry for that. We are supposed to put here the negative, okay, then you do this and you do that. When you compute everything, it will give you the 27/6. I hope we have answered your question. This one is the name. I hope Lucy's saying something like that. No, you will not be given. They will just give you to say, find the area bounded by this region. Sometimes they will sketch the graph for you already and then they ask you to find the area of the shaded region. Or sometimes they will give you a question and they will give you limits. Then you are supposed to do that. So no one will tell you to say this region lies below the x-axis or it lies above the x-axis or it's partially above the x-axis and partially below. When you are given a question, they'll just give you an open question. You are supposed to determine when. That's what I was saying. Make sure that you sketch. If you don't sketch that graph, then your answers will be wrong. So when you sketch the graph, you will be forced to find the x values. Those x values now are the ones that you're supposed to use as your limit. Sometimes you find a lot of x values, but then the region for which they're asking you to find its area is outside those other x values. Those other x values are outside that region, or they are not needed to calculate the area of that region as at that point of time. Okay, an example of this kind of a region is the region that I'm sketching here. So you have this region, which so an example of such a region like the one I've mentioned is a situation where this graph, the curve, is partially below the x-axis and partially above the x-axis. So you have a curve, something which behaves like this. It comes, then it goes down, then it goes up, so it starts coming down. So then they're asking you to find the area of the shaded region. Okay, now this region runs from point A to point B. Then you have C. So now this curve is y equal to f of x. So if you look at from A to B, from point A to point B,
just at 11 hours. Can you come again? I want to stand for this. How long is it? Is it a uniform?
Okay, so when you look at this curve, which is partially above the x-axis and partially below the x-axis,
the problem with okay, I can just tune. Yeah. So now we're going to
What time is the ending? What time is the ending? The test is at 11 hours.
no, you can just remove from now and then move that again in the morning.
Yes, my laptop. I hope it will print.
Just push this out there.
Okay, so this will mean the area shaded by the region, which is below the curve and the x-axis, it will be the integral from a to b of f of x dx. Now, if you look at the region from b to c, the curve is below the shaded region, so its area, it will be the negative. So in short, what you're doing is you are summing the areas. Now, because for us to calculate the area of the region which is above the curve, we take the negative of the integral of that curve from b to c. Now, if you look at positive by multiplied by the negative, is just the negative, so we just leave it as the minus there. So let's look at an example.
But if I disconnect, won't the PC go
My PC,
with the monitor?
disconnect is fine. Just disconnect the. Oh yeah, just disconnect is fine. I hope that thing will work. The laptop.
What am I disconnecting from this?
Can disconnect it. Okay, let's look at an example. This example says hello. Morning, can you call me at 11? I'm in class. Okay, let's look at an example number 7 from your notes, which says that this is example number 7. Example number 7, in which they are asking us to find the area bounded by the curve y equal to x multiplied by x minus 2, and the x-axis so we are finding the area bounded by the curve y equal to x squared minus x, and the x-axis, where the x-axis is running from x equal to -1 to x equal to 2. So now if you look at let's look at this example now. Let's look at the solution to this example. So they're asking us to find the area which is bounded by the curve y, which is equal to which is equal to x multiplied by x minus 2 from, now the x-axis, they are now telling us to say this x-axis is from x equal to -1 to x equal to 2. Now, let's sketch the graph of this function. The first thing is, before we sketch the graph of this function, when this curve meet the x-axis, so the curve, which is y equal to x multiplied by x minus 2, we will meet the x-axis meets the x-axis means the x-axis at x equal to 0 and x equal to 2. Now, if you look at our limits of integration, in this case now, like someone who asked to say, does it mean that when we are solving such a question that involves the area of the region bounded by the curve and the x-axis, we have to solve the given equation at a point where y is equal to 0, and then the x values that we get are our limits of integration? No, that's not the case. And like I mentioned, it depends to how the question has been given. Now, an example of such a scenario is the question which is given in example number 7. Here they are asking us to say, we need to find the area which is bounded by the region, this curve, which is of the region which is bounded by this curve, and the line x equal to -2, and also the line x equal to 2. Now, if you look at the point x, the line x equal to 0, this line lies between -1 and -2. Maybe let me sketch the curve. Graphically, the curve to the graph of this curve will look like this. So we have at 0, we also have at 2. Please, when you are given such a question, you're not supposed to draw the graph of that curve. You're just supposed to sketch it. It's not even necessary to find the turning point or what. Those are not needed. You already did those in the first semester. So all you need is just to sketch the graph of that curve and how it will look like. So now, at this point, we have a 2. This is the point where the graph will cross the x-axis. We also have the point 0, where the graph will cross the x-axis. But then, what the question is asking us is to find the area of the region bounded by this curve and the x-axis, where the x-axis is starting from x equal to -2 and x equal to 2. So if we can have our point here, which is the -1, and we extend this line. So the region we are talking about is this region, this shaded region. So if you look at the shaded region, this is the region which is bounded by the curve, which is partially above the x-axis and also partially below the x-axis. So then now, using that formula, so it means that the area of this region, which is bounded by the curve, which is partially above the x-axis and partially below the x-axis, this is equal to the integral. Now, our function f of x is x multiplied by x minus 2. Now, x multiplied by x minus 2 is the same as x squared minus 2x dx. Now, you need to be careful when you are selecting your limits of integration. Now, look, under this shaded, for this shaded region, in the interval -1 to 0, the curve is above the x-axis. In short, the region is below the curve. So we take the positive of the integral. So from -1 to 0, we take the positive of the integral. Then now, if you look at the other part of this shaded region, this other part, the curve is below the shaded region, or rather the curve is below the x-axis. So we take the negative of the integral from 0 to 2 of the function x squared minus 2x dx. Now, when you integrate these regions, what you're going to get is, we are going to have, when you integrate x squared minus 2x, what you get is x power 3 over 3 minus x squared. The limit of integration is from -1 to 0, then minus, again, you have x power 3 over 3 minus x squared. The limit of integration in this case is from 0 to 2. I hope everyone you are following with my explanation. So when you apply the fundamental theorem of calculus, what you are going to get, this part is going to give us 4 over 3 plus the other part is going also to give us 4 over 3. When you add this, we are going to get 8 over 3 units squared. Please, if you have any questions, we can start asking questions before I proceed to the other part. You can just type a question, I'll be able to see it. So then I explain, I clarify whichever points that you didn't understand. So in the next, before I go to the next part, I would sit to answer your questions for about 3 to 4 minutes.
that or still?
I don't know what's happening. I think it was stopping.
Okay.
So there's someone who's asking a question, Nancy. You are saying, unlike the other two x values where x is equal to -1, y is not equal to 0. Like I mentioned, it's not always that the limits of integration has to be the x value at which y is equal to 0. No. Y can be any value, but all you are interested in is the area which is covered by that curve and the x-axis. If you look at, like you are mentioning, if you look at, if you substitute in the equation x equal to -1, your y value here will be y will be equal to what? That is it will be 3. So your aim is not, your main goal is not to look at the y values. It's not to say, no, the only limits of integration that I need to have is a situation where only those x values at which the y ordinate is equal to 0. No. So yours is to look at the region which is being covered by the curve. So you like in the next session, you see a situation where we have this region which is bounded by two curves, and these two curves don't even at any point, will never even at any point touch the x-axis. So you will never have a point where y is equal to 0 when you sketch these two curves. So that region, it's not even below, it's not even bounded by the x-axis at all. X-axis is not part of that region, in short. Okay, any other question? More questions, please. Okay, since you don't have questions for me, then I'll continue. So let's now look at another concept where the area is bounded by two curves. Area bounded by two curves. So we are now going to look at area between this is 1.3 area between two curves. Which is definition number 8 from your notes. So we are saying if we have a function f and a function g, both continuous, which are both continuous throughout the closed interval, A to B, and in this interval, and within this closed interval, the function f is greater than or equal to the function g of x, then the area bounded between, so the area that lies between the curves, between these two curves, the first curve, maybe we can label it to be y1, y1, which is equal to so our y1 which is equal to f of x, and our y2 which is equal to g of x, from x equal to a, from x equal to a to x equal to b is given by area is equal to the integral from a to b. Now, if you look at the function f of x, the function f of x is always greater than the function g of x. So we are going to say times the area which is bounded from point A to B is equal to the integral from the point A to the point B of f of x minus g of x. Now, if we apply the linearity property, this will just give us the integral from A to B. So we are integrating with respect to x. So this is just equal to, when we apply the linearity property, it's the integral from A to B of f of x dx minus the integral from A to B of g of x dx. So provided you have been given this region, which is bounded by the two curves f of x and g of x, then its integral, then you need to look at which of those curves is greater than the other, then you need to apply this formula. Okay, let's look at an example. Now, graphically, maybe before I look at an example, let's look at its graphical structure. So, graphically, you have a region of this nature. So you have y, our y-axis, you have our x-axis. Now, maybe you have this curve that behaves in that manner, and then you have another curve, maybe that will come like that, and then it goes up, then it goes down, So basically, then they are asking you to calculate the area from the point A. This is our point A to the point B, maybe somewhere there. So we have our point B there. So then now they want you to find the first curve is the curve y1, which is equal to f of x. Our second curve is the curve y2, which is equal to g of x. Now, if you look at the function, all the values, whatever value of x that you substitute in g of x, the values of y that you get will be always less than the values that you get when you substitute that value of x in the function f of x. So now what they are asking you to calculate is the area of this shaded region. So the area of this shaded region is just equal to, moreover, if you say you can't recall the formula, if you say you can't really start, though some of you want to start memorizing the formulas, which is impossible. So if you see to read that you can't recall the formula, then the only formulas that you need to recall are those with a situation where the shaded region is above the curve, and also the situation where the shaded region is below the curve. Remember that when the shaded region is below the curve, then you take the positive of the integral. Now, when the shaded region is above the curve, you take the negative of the integral of that function, which is below that shaded region. So when you combine these two, it means what you are finding is the area which is bounded between these two curves. Okay, let's look at an example. There is example number 9 from your notes. Let's look at example number 9 from your notes. So I'll just look at one example, then we'll go to volume of revolution. So the example says, this is example number 9. It says, find the area of the region enclosed by the parabola. So we have this area which is enclosed by this parabola and the line. So you have this region that is bounded, which is enclosed by this parabola, and the line y equal to negative x. Now you have this question, and then they ask you now to calculate the area which is enclosed by the parabola x equal to, y equal to 2 minus x squared, and the line y equal to negative x. So before you even start doing anything, the first question that you need to understand is, when will this curve meet the x-axis? At which point will this curve meet the x-axis? So if you look at this curve, the curve, before we look at the straight line, if you want to sketch it, when will the curve meet? Because you can't sketch this curve without you knowing when it will cross the x-axis. So the curve, I'll just write that because all of you knows we did quadratic functions. So the curve meets the x-axis at x, when x is equal to plus or minus the square root of 2, which is just 1.7 something. So these are the points at which to meet the x-axis. Then now, what will be the turning point? The turning point will occur when x is equal to 0. So when x is equal to 0, that means the turning point will be 0, it will be 0,2. Now, maybe let me wrap the other part so that I can sketch it from here, then I leave the other part for solving. So graphically, graphically, we have something like this. So our curve will meet the x-axis at, so we have 1, we have 2 there, we have -1, we have -2 there. The turning point will be, so we have 1, we have 2, so those are enough. So this curve will come like that, will pass through the 1.7 something, because the square root of 2 is 1, should be 1.1 something. So here we have the square root of 2. Here also we have the square root of 2. So this region, this curve is the graph of the curve y equal to 2 minus x squared. Moreover, if you look at the coefficient of x, the coefficient of x squared is -1, so we are going to have a maximum turning point. Now, we need also, then after you've sketched the first curve, remember that the region that they are asking you to find, its area is bounded by two curves, the linear curve and the quadratic curve. So the line y equal to -x is a straight line that is passing through 0. So it's that line that passes through 0. Now, the region they want you to find its area is this shaded region. So that's the region they want us to calculate its area. Now, when we were still at high school, they were just asking me to count the number of squares, but now we use integration. So this line is y. This line is y equal to -x. So this implies that these other points are not necessary, because the point that we need is just that region. Now, the other thing that you need to understand is that what are the limits of integration? So this is also another point that we need to understand. What are then our limits of integration? So now if you were solving this question, now you are a bit stuck. You start now thinking of what would be my limits of integration. So this is the most important part that you need also to find. Now, how can we find the limits of integration? So in this scenario now, if you want to find the limits of integration, you have to solve the two equations simultaneously. So the limits of integration will be at the point, it will be at this point. So you have to find the x value as at this point. So you have to find, so you go to the point where these two curves are meet. It's at that point and at that point. Now, it means you have to read the x values, of which we don't know what these x values are going to be, because in this scenario, our sketching is not that accurate. So you go to the points where these two curves are meeting, then you read it. Now, how can you find the values of x at those 2 points where these curves are meeting. So all you need to do is you need to solve these 2 equations simultaneously. So to find the limits, solve the equations, we need to solve the equations simultaneously. So we solve the equations, these 2 equations, so when we solve these 2 equations simultaneously, then you were able to find the values of x for which these 2 equations intersect. Now, how can we do that? So now, to solve these 2 equations simultaneously, the 2 equations are y equal to 2 minus x squared, that is your equation 1, and y equal to negative x, that is your equation 2. So if you look at these 2 equations by substitution, so the simpler way is to go with this is you use the substitution method. So by the substitution method, what we have is by substitution method, where there is y in the first equation, we substitute a negative x. What we have is a negative x is equal to 2 minus x squared. When we simplify this, this will give us x squared minus x minus 2 is equal to 0. When we solve for x, what we are going to get, this implies x is equal to negative 1 and x is equal to negative 2. Alright, so after you find, this now becomes your limit of integration. Hence, so in this case now, our a is equal to negative 1 and our b is equal to 2. Now, when now you do the integration, you have to be careful. Remember I told you that you have to be careful. So now, in this case now, then the area, that shaded area is just equal to the integral, okay, from point A, oh, the other one is positive 2, from point A, which is negative 1, to point B, which is 2, of, okay, now, I would wish you to split this in advance, because it's, even if we try to do step by step, it's just one and the same thing. So is equal to the area, so it's, you get first, look at the first curve. The first curve, let's look at the first curve. Okay, let's look at the first curve. Alright, so the first curve, which is equal to y equal to 2 minus x squared, the shaded region lies below the curve y equal to 2 minus x squared. So then the integral here, under this curve, we are going to take the positive integral of 2 minus x squared dx. Now, the second curve, which is the line x equal to negative, y equal to negative x, this line, it lies below the shaded region. So the shaded region is above. So we take the negative of the integral. Again, if you look at the limits of integration, here in this case now, the limits of integration are the same, from negative 1 to 2. Again, for the curve which is above, it's again from negative 1 to 2. Okay, so we are going to have our in this case now, our f of x is just equal to the negative of x dx from negative 1 to 2. Alright, now when we simplify that, I'm now wrapping this region. So when we compute and applying the fundamental theorem of calculus, when we compute that by applying the fundamental theorem of calculus, so what you're going to arrive at is, so when we compute that, what you're going to get is, remember, negative times negative is positive. So, or if we use the linearity property, since the limits of integration are the same, if we use the linearity property, that is just the same as the integral from -1 to 2 of 2, then minus x squared, then plus x dx. Okay? So, because the limit of integration are the same, so we can combine these two, but this negative times negative is positive, that's why it's giving us a positive x. Now, this is going to give us, when we do the integration here, we are going to have 2x minus x power 3 over 3 plus x squared over 2, then from -1 to 2. When we simplify this, when we push in the limits, what we're going to get is that we are going to have 2 multiplied by 2 minus 2 cubed over 3 plus 2 squared over 2, using the fundamental theorem of calculus, minus, when we apply, it will be 2 multiplied by -1 minus -1 to the power 3 over 3, then plus -1 the power 2 over 2. So when you simplify this numerically, what you're going to get is you're going to have a 9. So this will be equal to 9 over 2 units squared. So we are going to have a 9 over 2 units squared. Then you are done with your calculations for finding the area which is bounded by the two regions. For more examples, I would ask you to go through the notes. So for more examples, I would ask you to go through the notes, because the notes has a lot of examples, and the textbooks that I sent to your groups. Okay, having said that, so now when I was explaining, most of the time we have looked at the area which is bounded by the curve and the x-axis. Most of the time we were usually having a situation where the limits of integration are the x values. Now, what happens if you have, let me ask you, you've done coordinate geometry, you did coordinate geometry in the previous weeks, should be after vectors or before vectors, you did coordinate geometry. Now let's look at, let me take you back, you recall back from the coordinate geometry point of view. Now, if I give you a scenario like this one, let me just, so basically what we'll now be looking at is the area bounded by the curve and the y-axis. Okay, we'll just look at some parts. Let's look at the area bounded by the curve and the y-axis. So this is 1.4. We are looking at area bounded by the curve and the y. So area bounded by the curve
the curve y equal to f of x, and with respect to the y axis.
So let's have a situation where we have this area which is bounded by the curve and the y axis. So we now look at the area bounded by the curve and the y axis. So also if f and g are continuous in the entire interval a to b. Now in this interval, whatever value of x that you pick from this interval, the function f here now of y is greater than or equal to g of y. It's in the interval c to d, and no matter what value of x, of y that you pick in this interval, the curve, the values of f of y will always be greater than the values of f of g of y. Then the area of the region, the area of the region, then the area of the region between, here now we say between x equal to f of y and x equal to g of y is given by, now remember the parabolas and hyperbolas, right? That's one thing you should remember from, is given by the integral. So this area is given by the integral from c to d of f of y minus g of y. So f of y minus g of y dx. So the area of that region will be the integral from c to d of f of y minus g of y, which by linearity properties, this is just the integral from c to d of f of y with respect to y, not with respect to x, sorry for that, minus the integral from c to d of g of x with respect to y. We have g of y with respect to y. So now this is the formula that we'll be using in a situation where they are asking you to find the area which is bounded by the region with respect to the y-axis. An example of such region is the region that I'm sketching here on the board. So examples of such regions are as follows. So such a region like this one. So if you look at this region,
graphically, maybe you have a region like this one, you have this curve, then you have also this curve which comes like that, and then it goes like that. Then now, they're asking you, maybe this curve, this one is x1, which is equal to g of x, and this one is x, or this is x1, which is equal to f of x, and this one is x2, which is equal to g of x. Now, they are asking you to find the area which is bounded by this region from the y-ordinate from the point this point y equal to c, from the point C, so this we have a C here, to the point D. So then the area bounded by the region between x equal to y and x equal to g of y, from y equal to, so we say here, we say from y equal to c to y equal to d, which is this region, is given by this formula. Another structural graph of such kind of a region is the region also I'm sketching down here. So they are very special regions. So we have the y, we have the x-axis, we have the x-axis, then we have the y-axis. So another kind of such a region, for example, maybe we have a region like this curve comes like that. It's a parabola. It's a hyperbola. It's a parabola. Then you also have another region which comes like that. Now, so in this region, I'm in class. So in this region, I'm in class. So in this region, what you can do is so this part becomes our f of x. So this part becomes our x, which is equal to f of x, and the one which is on the left hand side becomes our x, which is equal to g of x. Now, you realize that where these 2 points are meeting, they will give you your y values, which is c, and there we get d. Then now they ask you to find the area of that shaded region. So when finding the area of this shaded region, if you look at the way this graph has been sketched, you cannot make your limits of integration to be the x ordinates. Instead, to make your life easy, to make your work fast and easy, you should change your limits of integration to be the y values. Okay, I hope everyone is following with my explanation. No one is behind. So let's look at an example now that involves such a scenario, such a situation, such a case where you use the y values as your limit of integration. Okay, so let's look at an example. So there will only be one example that we are going to look at. Then okay, so let's look at example number 12 from your notes. Example 12 from your lecture notes. From your lecture notes, this question says, find the area enclosed by the line. So we need to find the area enclosed by the line y equal to x or y is equal to x minus 1, and the parabola y equal to y squared is equal to 2x plus 6. Or rather, I would wish to say the square root of 2x plus 6. So now we can't sketch the graphs if we don't know how this curve looks like. But the first thing first is you are supposed to find the points at which these two curves intersect. So to find the points at which these two curves intersect, it means you are supposed to solve these two equations simultaneously. Okay, which I would say you are going to do yourselves. So by solving the two equations, by solving the two equations above, once we solve these two equations, so when we solve the two equations, the point of intersection, the points of intersection, when we solve the equation y is equal to x minus 1 and y is equal to the square root of 2x plus 1 simultaneously, you are going to find that you are going to have x is equal to negative 1. Now when x is equal to negative 1, your value of y will be negative 5. And also you are going to find that your x will also be equal to 5. And when your x is equal to 5, when you substitute x equal to 5 either here or here, your value of y will be equal to 2. Oh, sorry, it's supposed to be 4. Okay, okay, now, after you have found this, now, we need to change the variable of integration, because maybe before we do that, let's sketch the graphs. When we put where there's x is 0, maybe before I come to now go into the solving process, let's sketch the graph and see what do we have at hand. Let's sketch the graph and then we see what we have at hand. That's when now we can decide which part should we, what kind of, do we integrate with respect to the y or with respect to the x. Okay, now, so if you look at the graphical structure of that region which is bounded by those two curves, the graphical structure is graphical structure okay. Okay, this is the graphical structure of the region. So now if you look at the first one, we need to make x the subject of the formula here. So note y equal to x minus 1. This implies x is equal to y plus 1. And y is equal to the square root of 2x plus 6. When we solve for x in this equation, what you're going to get is x is equal to y squared over 2 minus 3. Okay, now you remember we did the parabolas and hyperbolas where I think you did a lot of stuff concerning parabolas and hyperbolas, that opens upwards, that opens from the left, that opens from the right. You did all such things. So graphically, you have something like this, which comes like that. You have a curve that comes like that, then it starts going. So you have this hyperbola, or this parabola that opens to the left, and you have this line x, which is equal to y plus 2. So when x is equal to 0, y is equal to negative 1. So we have something there. When x is equal to, when y is equal to 0, we have x equal to 1, we have something there. So we have also this straight line which cuts that point. So now, so what we have, this one is x equal to y plus 1. Then this curve is x equal to y squared over 2 minus 3. So the region now, which they are asking us to find its area, is this region. So that is the region. Now, when we solved these two equations simultaneously, so we had found negative 1 comma the point where they meet. I think this one was supposed to be negative 2. Sorry for that, because if we put negative 1 here to give us negative 2, sorry for that. So this point is the point negative 1 comma 2, and this point is the point 5 comma, we have a 5 here. This point is 5 comma, so we have a 4 there, so we have a negative 2 here. Okay, now then when we apply, so these curves will meet at negative 1 comma negative 2 and 5 comma 4. But now, looking at the way the curve has been given, yes, you can use the limits of integration to be y. You can use here, you can even use the x as being limits of integration. Now, let me tell you something here. If you use x as your limit of integration, one thing that you should remember is that then you need to split this curve into a lot of components. One, from here to here, if you draw a straight line here, so it now you have also to find what the x coordinate, this point where it will cross the when y is equal to 0, so your x is equal to negative 3. So this point basically is negative 3. Now so it will be from negative 3 to negative 1. You have both down and up. Then from negative 1 up to somewhere here, up to 2, is this point? No, up to 1, you have both this curve and this line. Again, so this curve is below this line. Again, you have from 1 to 5. So you have all these scenarios now. That means you need to demarcate this region into 3 sub-regions if you want to use the limit of integration to be the x values. Now, since we are able to find the y values, that will make our life easy, that will make your work easy. So you don't need to start demarcating this given curve into components so that you can use the limit of integration to be the y values. So we can just use the x values. So we can just use the y values. I can assure you the final answer that you're going to get to be the same. So I'll maybe impose that to be an exercise. When you sit, use the x values as your limit of integration and then compute. Then you're going to see what you're going to get. You're going to get the same answer at the end of the day. Now, so after we have sketched that, then now we are going to say now that so then we have so when we now integrate with respect to y, what you're going to have is that then the area now will be equal to the integral. Now it will be from -2 to 4 of the first function. Our first function is what? This one. Okay? Now what is this function? That's the question you should ask yourself. What is that function? Now, I did not mention something here. Here now, if you use your x values as limits of integration, this line is below the shaded region, and this one is above the shaded region. Now, because we are using the y values as being our limits of integration, you look at these two curves. If you look at these two curves, which one of these two curves is on the right hand side of the shaded region, and which one of these two curves is on the left hand side of the shaded region? Now if you look at the curve x equal to y plus 1, this curve is on the right side of the shaded region, so it's the one that you are going to start with. So we are going to have y plus 1 dy, then minus, because this other curve, if you look at it on the left side of the shaded region, so we are going to have it to be the second part of our, so it will be from -2 to 4 times y squared over 2 minus 3 dy. Now, because the limits of integration are the same, we can combine these two, and we are going to have, when we combine these two, we are going to have y plus 1 minus y squared over 2 minus 3, everything dy. When we simplify further, we have the derivative from -2 to 4. Okay? So when we rewrite this, we have the negative of y squared over 2, then plus y, then plus 4. Okay, dy. When we integrate with respect to y, once we integrate with respect to y, so what we are going to get is, when we integrate this with respect to y, what you are going to get is that we are going to have the negative 1 over 6 y to the power 3 plus y squared over 2 plus 4x from negative 2 to 4. When we apply the fundamental theorem of calculus, what you're going to get, the whole of this is going to give us 18 units squared. So we are going to get 18 units squared. Okay. So any questions, please? On area. This is 11 hours. Any questions on area? We need to break. I'll come and finish the part for volume in the afternoon. So because this is 11 hours, so we can end here. So anything to do with the area of integration, we are done. So we are just remaining with the part to do with the volume. When we are done with that, then I think in the afternoon we'll see how much time we have. Maybe we'll also look at some applications of differentiation, just a few, not a lot, just a few of them. We'll just sample some, then we call it the end of this class. So we said, so either on Tuesday or on Monday or on Tuesday you're writing your test. On Wednesday, your CS should be out before you go into your exam rooms. So please make sure that you prepare. I'll post to the group before the end of today, Monday or Tuesday. Before, when I decide, I'll make a decision on which day you're going to write your test 2. All right, enjoy your day. We'll meet at 14 hours. So today, 14 hours, we are meeting. Please don't say you postponed. I'm not postponing. So today at 14 hours we are meeting. Please go through those notes that from what I've explained. When we meet at 14 hours, in the first 30 minutes, I'll not make any delayments, provided internet will be there. I'll not make any delayments. Say, no, let me wait a bit. 14 hours exactly, I'll start. And I'll not post anything to your group, say, no, I've started. So I've already mentioned to you that 14 hours I'm starting the class. Let's make sure that we buy some bundles so that we listen to the last session of calculus. Thank you so much for your time and enjoy your lunch.